Okay, so I want to continue on and work out part E of the strong acid, strong base titration that we started on in class today. So let me remind you of what's going on in your flask. So we were titrating the acid. In this case, it was nitric acid, a strong acid, and we had already determined that in the beaker or in the flask, we had a total of 10.0 millimoles of the acid in this beaker. Now you were titrating that with a strong base. So remember, from the strong base is the hydroxide ions that are going to react with the hydrogen ion. Now in this part of the titration, you are adding 150 milliliters total of 0.1 molar sodium hydroxide. So remember, we need to go figure out our millimoles of sodium hydroxide that we're adding. So the millimoles of sodium hydroxide is going to be calculated by taking the molarity times the volume. So the molarity is 0.100 molar. The volume is 150 milliliters. So that means for the hydroxide ion, we have a total of 15.0 millimoles of hydroxide ions that we are adding to the flask that contained 10 millimoles of the acid. All right, so now we're going to do the stoichiometry. Remember, the net ionic equation that we're going to use for the strong acid, strong base titration is hydrogen ion plus hydroxide ion in equilibrium with liquid water. So we're going to ice problem here and fill in our millimoles. So we have 10.0 millimole of hydrogen ions. We just figured out 15.0 millimole of hydroxide ions. And the water is a liquid. So remember, at this point, we subtract the smaller amount because the stronger substance is going to completely react with the substance that is in the greatest millimoles is going to completely react with the one in the lesser millimoles. Now, up to this point, our smaller amount had been the hydroxide ion, but we passed our equivalence point. Remember, in part D, we were at the equivalence point. We have a neutral salt that's formed. The only thing left here is pure water at this time. So the pH of pure water is going to be 7. So after you pass the equivalence point, now the base is in control of the pH. So you're going to subtract 10.0 millimoles from both. And that's going to leave you with none of the hydrogen ion, and it's going to leave you with 5.0 millimoles of hydroxide ions. All right, we still need to calculate our total volume. Remember, V total is determined by taking the volume of solution that was in the flask to begin with. And we were told that to begin with, we had a total of 50 milliliters of the acid solution. We just added 150 total of the base. So that means our new volume is 200 milliliters. All right, so we need to now figure out the hydroxide ion concentration in this flask. So we're going to take the 5.0 millimole, and we're going to divide that by the 200 milliliters. And that's going to give us our new concentration. And this time we're finding the concentration of hydroxide ion. So at this point, when you divide, you get the concentration is 0.025 molar. And that is the concentration of hydroxide. So The pOH is what we're solving for here, a negative log of 0.025. When you take the antilog of 0.025, you get 1.60 for the pOH. Always be aware what you're solving for. And that means that the pH is 14 minus 1.60, which is 12.40 for the pH, which would be your final answer on this part E. Now, just to remind you, look at what's happened to our pH throughout this titration. We started off when we had just an acid at 0.699. As we added base to the solution, the pH started to rise. It went to 0.82 in part B. In part C, it went to 0.94. Notice it rapidly rose to the equivalence point here, 7.00. And then now that we've added 50 milliliters more, so 150 total, it's up to 12.40 for the pH. So if you were to look at the titration or the values you would have there, and you plot the pH curve, your titration curve that we talked about, you would notice in a strong acid, strong base titration that you have, this is that general shape, we're talking about the S shape of the pH curve or the titration curve. pH is plotted here. Notice this was at the end point, the equivalence point. Now this particular one here is showing you hydrochloric acid with sodium hydroxide. The titration we just did was actually nitric acid, but either way, you would still have the same general shape. Notice how it's very symmetrical. With a strong acid, strong base titration, the pH at the equivalence point is always 7. Now, if you were to have titrated the strong base with a strong acid, notice your pH would have started off high. If you start in your flask with a base and you're putting an acid from the burette, the pH would start to lower, and then again at the equivalence point the pH would be 7 for the strong titration, and then the pH would continue to lower. Now in this case here, this is titrating from the burette. You would have had the hydrochloric acid, and into the flask you would have had the strong base sodium hydroxide. Okay, and you're always monitoring the pH of what was in the flask. So that's why it starts off at like high pH, and then as you add the acid, the pH lowers, and you can plot your pH curve. Okay, so that's a strong titration.